EDX Core Pure, Vectors 3, Equations of Planes. The equation of a plane in parametric form. The vector equation of a plane. We've already seen that there is more than one way of writing the equation of a line in 3 dimensions, and the same is true of the equation of a plane. So in this recording we're going to look at writing the equation of a plane in the parametric form, and we've already seen the use of the parameter lambda when we wrote down the equation of a line in 3 dimensions, and we're going to use a similar idea for the plane. The parametric form is a convenient form when you know either 2 direction vectors that lie on the plane along with a point on the plane, or when you know 3 points in the plane. The parametric form can be very useful in these 2 circumstances. So this is the general parametric form. If we know the position vector of a point on the plane, usually called little a, then we can get ourselves onto the plane. We can then use multiples of 2 non-parallel vectors b and c to get around the plane. So in this diagram, vector a is getting us onto the plane. Direction vector b allows us to move along the plane, and a different non-parallel vector c allows us to move in a different direction on the plane. So if we travel along a to get to the plane, and we can travel along a scalar multiple of b, we can move in one direction. In other words, we could walk in a straight line. But if we can also have a different scalar multiple of c, we can move in a different direction. In other words, we can move around the plane. And we're going to have a look at a GeoGebra file to see how the values of vectors a, b and c determine what the plane will look like. So here you can see the GeoGebra file, and we can now have control of the vector a, which gets us, that's the position vector that gets us onto the plane. We can control the direction vector b and the direction vector c. So if first I change a, you can see that moving the position vector defines a different plane. If I change the direction vector b, I can also change what the plane looks like. And if I change the direction c, the vector direction for c, I can also create a different plane. So b and c are vectors that direction vectors that move along the plane, or they're displacement vectors, and a is a position vector which determines what the plane looks like. The other interesting thing to note, if you look at the equation of the plane in the top left hand corner, the coefficients of x, y, z match this normal vector, which is the black vector you can see on the diagram. So if I start changing a, the normal vector changes, and if you look at the coefficients, they will always match the components, the ijk components of the normal vector. So a is the position of a point on the plane, which I can change. B is a direction vector, which I can change, and c is a different direction vector I can walk along to define the plane. So in this example we've been given the coordinates of 3 points on the plane. In other words, we know 3 position vectors. We know the position of the point P, the position of Q and the position of T, and we can use these 3 points to define the plane in parametric form, where lambda and mu are the parameters we're going to use. There are various ways of setting out this equation, but the position vector I'm going to use for a point on the plane, I'm going to use OP as my position vector. I'm going to use P to Q as one of my direction vectors that I'm going to walk in, and I'm going to use P to T as a different direction. So OP is the thing that we've been calling little a in our formula. P to Q is going to be the thing that called little b in our formula, and P to T is going to be the thing called little c in our formula. So A is the position vector, B is a direction vector, C is a direction vector. So we need the position of a point on the plane, and I'm going to use 1, 2, 0. I could have used the position of Q or the position of T. For one of my direction vectors, I'm going to use the vector from P to Q. So that's -2, -1, 3. And for another direction vector, I'm going to use the vector from P to T. So that's -1, 1, -1. So to get to a general point on this plane, so I'm going to call that R, I need to get from the origin to the plane, so that's OP. I need to be able to walk along a multiple of PQ, so that's lambda PQ. And I need to be able to walk in a different direction, so that's PT, and I need a different multiple. I can't use lambda again. So a general point on this plane can be represented by the position of P plus a parametric multiple of the direction vector PQ plus a different parametric multiple of the direction vector P to T. So that is one way of representing the vector equation of this plane. And we can see the clear detail there. In the next session, we're going to be looking at the equation of a plane using the normal to the plane.